pandemic forbid us for a while to gather as we were used. But luckily, we were not forbidden to keep doing research, to keep doing teaching, and keep doing all our activities from home in a different way. But that was still, we were all able to continue to collaborate and to promote research. I'm very happy to say that we have participants from Colombia, Chile, El Salvador, US, Uruguay, and Mexico. I was saying more than 60 people are enrolled in this school. This school, as you know, is focused in introducing to graduate and young researchers to the recent connections between p-adic analysis, understood in a very large sense, with mathematical physics and computer science. And that is, I think, very interesting for us because it represents several areas of CIMAT, several possibilities of collaborating in between these areas of research and also with several institutions in the world. So we have 6 mini courses and several talks that will be offered. Some of the speakers are from here, from CIMAT, and from all the other institutions. And I must say that Cimpa School are very important for us. Actually, I would like to thank our representative. You will speak now? Yeah? Okay. So the CIMAT, the Cimpa schools have always been very important for CIMAT because it has been a very nice way to promote research, to introduce young researchers and students to these hot topics in research in mathematics, and we have been organizing many of them here in CIMAT in either of the antennas we have, and this is also a very good way to build institutional relationships, to build and foster new research groups, and something that is also important for us is to attract students to our graduate programs or just keep doing mobility. So spend some time here in CIMAT doing some research. I hope you will enjoy very much your time here in Guanajuato, either connected or presentially. And we hope also you will be very much interested by the topic of research, and that this will help to keep you connected with the topic and the research groups that are being represented here. And I like to thank the organizers, the main organizers, Academic Committee, Wilson, thank you for organizing this school, the local committee, Manuel, Rogelio, Edwin, thanks to all of you. And I don't want to speak much more. I hope you will enjoy very much of this school, and I think the main organizers will have more things to say.
Thank you. Thank you very much. I just want to thank the local organizer, Dr. Manuel González Villa, Dr. Rogelio Pérez Buendía, and Dr. Edwin León for organizing the conference. Thank you very much, guys. Also, I want to recognize the support of CIMAT and Cimpa. Thank you. Now, Dr. Joan Lario, the representative of Cimpa, is going to say some words.
Okay, thank you. I'm going to be very short. I'm very discreet as the periodic evaluations. And just to thank the students that you have come to attend this school. I think this school should have been held in 2020 maybe. But now, as we all know, the good things make us to wait. And so I'm very sure that, let's say, Hensel and Kummer will be very proud for this school. No? I wish the best for this school. Thank you.
Thank you very much. Now we are going to begin with the conference, with the course Introduction to P-adic Analysis. Today, Professor Trond Gernet from Norway is going to give an introduction to the P-adic numbers. Please proceed, Trond.
Thank you. Let me share my screen here. Let's see.
¿Le puede pedir que se acerque un poco más a su micrófono, al ponente, por favor?
Okay. Can you see my screen?
Yes, we can see your screen, Trump.
Okay, thank you. Okay, so I'm going to have the first part of this introductory course, and I sort of try to give a very gentle and soft introduction to this material.
Yeah.
Because after all, it's a very unusual topic with some.
Trump, can you increase the volume of the microphone, please?
Sorry,
Or get closer to the microphone?
can you not hear me?
Yes. Yes, but could you please get closer to your microphone and increase the volume of the microphone?
Well, the microphone is up there, and I don't know if I can get any closer to it, but it's the microphone is on top of the screen. Is it better now? Hello.
Aquí ya está todo.
I mean, we can hear it.
Okay, okay. Okay, let's proceed, Trump. Go ahead.
Okay, shall I try? Okay.
Yeah, please.
Okay.
Yeah.
Okay, I'll try. So yeah, so I'm going to have the first part of this introductory course, and Wilson will take the second 2/3 of it. I'll take the first third, and he take the last 2/3. So I decided to try to give a very gentle and soft introduction to p-adic numbers, because after all, they are a very unusual subject with some unusual features. So I would like to spend some time on these things, and then Wilson will take over with some more, with some harder stuff, maybe. So let me start. Here's a summary of what I plan to do. Start introduction, and then absolute values and completion will be discussed, and local compactness, total disconnectedness. I'll talk about additive characters and dual group and self-duality. And then I want to close with some examples with congruencies and fixed points. So with some history, the p-adic numbers, they were invented by Kurt Hansel in 1897. And they have played an important role in number theory ever since. And in physics, that's a more recent phenomenon. It started with Igor V. Wolowitz in 1987. He was at CERN in Switzerland, in Geneva at the time, and he found out there were certain features about physics at the level of the Planck scale and below, which was very difficult to describe by Archimedean methods or Archimedean geometry. So he proposed that at that level, one could maybe with use non-Archimedean constructions such as the p-adic numbers. So in physics, this is a fairly recent theory. It's only like 35 years ago. So let me start by mentioning that ordinary real numbers, they can be written in this form with in base 10, which is the most usual base. It's like that. And we notice that we always have a finite number of coefficients before the comma, and usually infinitely many entries behind the comma, so in infinitely many decimals. And this, if you require that the digits a, k lie between 0 and 9, then this presentation of a real number is virtually unique, except there are some, in some cases, those which end with a power of 10, they have exactly 2. Those which end with 0, I should say, that 0 can be replaced by infinitely many lines. Now, in the p-adic case, we're going to turn this around. And we are sort of going to have Yeah, okay, well, first of all, let me just say that what I just said about representing real numbers in base 10, we can equally do it with any other positive integer. And for example, with any prime number p, so you can do it like this. And once again, we have finitely many entries on one side of the comma and infinitely many often on the other side, on the decimal side. So now when we now are going to introduce the p-adic numbers, we're going to turn this around. And we're going to have only finitely many numbers, what we used to call behind the comma, but they are actually now written as being before the comma. And after the comma, we now have high powers of the digit p. So I mean, the part which has low powers of digit p, there are only finitely many of those. But that part which contains high powers of p, they will usually be infinitely many. And this looks a bit strange because, you know, if you have a series like the one written there, ak p to the k, that doesn't seem to converge at all. And it doesn't if you use the usual absolute value. So we have to introduce a new absolute value, which gives sense to a sum like this. So that's the first thing we do. We're going to introduce a new absolute value on the set of rational numbers. So we start, So we start with introducing a new absolute value on the set of rational numbers. And we do it like this. So if you have any rational number x equal to a over b, we can factor out all the p's in the a and the b, factor it out, and you can write it as p to the n, a prime over b prime, where now there are no factors of p left in a prime or b prime. So this is a unique way of doing this, and so that exponent n is actually uniquely given by the rational number x, and we call this the valuation of x, and often written as nu x. And so when we have this valuation, we define a new absolute value on the rational numbers by saying that the p-adic absolute value of x is p to the minus the valuation of x. So yeah, so that means that let's say natural numbers like high or high value like 1,000, they will have a small p-adic absolute value if it has many factors of p in it, right? So this is a new strange feature, but this is how we do it, and we'll see what kind of consequences that has. So this new absolute value, it has all the properties of the usual absolute value, the one we are used to from the real line, as you see listed at 1, 2, and 3 there. And but then this new absolute value, the p-adic one, it has a version of property 2, which is stronger, and which says that the absolute value of x plus y, not only is it less than or equal to the sum of the absolute value, but it's also less than or equal to the maximum, to the larger of the two absolute values. So this is a more strict requirement on the absolute value, and any absolute value which satisfies this requirement is called non-Archimedean or ultrametric. Okay. So as soon as you have an absolute value on a space, you can define a metric, and we do it like this. So we can define a new metric on the rational numbers by saying that the distance between x and y is the p-adic absolute value of the difference between the two. So now we when we complete the rational numbers with respect to the usual absolute value, then we get the real numbers. When we complete the rational numbers with respect to this new absolute value, we get what we call the p-adic numbers, which is denoted by Q sub p. And there is a theorem by Ostrovsky which says that up to equivalence, there aren't any more absolute values on the set of rational numbers. So that's a quite remarkable fact. So they are sort of given by nature. So, okay, so now we have defined what they are, and then let's look at some special features, some very strange features about this geometry which you get from the p-adic absolute value. If you look at the first one, it says that if you have a triangle and where you have at least two sides which are not equal, then the third side is equal to the larger of the two sides you started with. So that's one, and that means that any triangles is actually isosceles. And it also has the consequence that any point in a ball is actually at the center of that ball. And if two balls intersect, then one has to be contained in the other. And property 4 says that if you add, if you start with any rational number, or for that matter, any p-adic number, and you add it up n times, and no matter how big this n is, the absolute value of the sum will never exceed the absolute value of the x you started with. It could be less, but it will never be bigger. And then we have a property which is sometimes called the calculus student's dream. And it says that if you have an infinite series, which is such that the nth term tends to 0 with n, then the series actually converges. And this is a very nice feature, which of course, we do not have in the real case. Just take the series 1 over n, which where the n term goes to 0, but the series diverges. But in the non-Archimedean world, all we need is that the nth term goes to 0. And that is a consequence of this. So since since we are at the very elementary level of this course still, let me give some proofs of these things, just to see how, just to get used to some kind of features we're using. So for example, the first property, we said that if you have one side strictly bigger than another, then the third is equal to the larger. And it's just this, that it's a usual trick that if you take the norm of x, you can insert a y plus or minus y, and you use this non-Archimedean property, and then you end up with this. So what this says is that the norm of the sum is squeezed between the norm of x on both sides, so they must be equal, and the norm of x was the larger of the two, so it means that the third side is equal to the length of the larger of the first two. And similarly, this thing about if you start with a ball, we call it BA, R. That is the set of x's in QP such that the distance from R is less than or equal to R. Distance from A is less than or equal to R. And if I take any B in that ball, I want to show that the ball with the center at B is equal to the ball with center at A. So let's do that. Let's start with the B in the ball with center at A, and let's see what happens. If you now start with an X in the ball, the center of A, and we want to show that this is less than or equal to R, then we have that the distance from X to B is, you can write it like this. You insert a plus and minus A and use the non-Archimedean property. And both of these are less than or equal to r because x is assumed to be in BAR, and B it was given to be in BAR, so they're both less than or equal to r. And so that means that if x is in BAR, then x is in BBR. Okay. So you get that the ball, so BAR is contained in BBR, and then by symmetry, you also have the reverse inclusion, and hence equality. So let's prove the last one also, that if two intersect, one is contained in the other. So let's say that you have two balls with center at A and B, and with radius R1 and B, R2. And let's assume that R1 is less than or equal to R2. And they claim that the BAR1 is contained in BBR2. So to do this, what you do is that you measure the distance from A to B by going via that point Z in the intersection. So let's see what happens. So you start with an X in the ball with a smaller radius, and you want to show that it then lies in the ball with the bigger radius. So you measure the distance from X to B, and then you insert plus minus A and plus minus Z, where C is in the intersection, and you get a maximum of 3 quantities, and they're all less than, so this one is less than R1 by assumption. This one is less than R1 because C is in the intersection. And this one is less than R2 also because C is in the intersection. So you get this. And then if you start with this, you get that X minus B is less than R2. So then, so then you get that X is in BBR2. And so BAR1 is contained in BBR2. Okay. I don't know. Maybe are there any questions? I maybe, or are people used to these things? I mean, have they seen pianic numbers before? So,
are there questions? No, there are no questions from.
Okay, then I go on. And I hope people can hear me. And if you don't hear me, at least you can read the slides like this. So. Okay, so as I mentioned, in QP, if you have a series where the nth term, or the k term as it's called here, then goes to 0, then the series actually converges. And that follows from this ultrametric property, namely, what you show is that the partial sums, call them Sn, they form a Cauchy sequence, because if you look at the partial sum up to n and m and take the difference, and then m is bigger than n, and then use the ultrametric property. Oh, okay, there's a misprint there. It should not be a plus there, it should be a comma, dot, 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 comma. And by assumption, these are all less than epsilon because everything here has an index larger than the capital N. There should be a comma there and there. Okay, and so that means that the partial sums form a Cauchy sequence. And since QP by construction is complete, then the series converges. Remember that QP, the p-adic numbers, they are the completion of the rational numbers with respect to the p-adic norm or the p-adic absolute value. So it's a complete metric space. Yes, so that's one thing. Now, if you, in addition, put some extra conditions on these terms, for instance, if you look at the series of the form xk, p to the k, and k start from a certain n, this n could be negative, or it could be positive, or it could be 0, okay? But it's any finite integer, and it goes to infinity. If you look at the sum like this, then the k term here goes to 0, because because the normal of the k term is actually p to the minus k. And because the normal xk itself is 1, because it lies between 0 and p minus 1. And so the normal of the k term is less than or equal to p to the minus k. And so this goes to 0, and therefore it defines an element of QP. And conversely, if you start with any element of QP, it can be written this way or in this form. More precisely, we have the following. Namely, that if you start with any x in QP, and if you then put p to nu of x, remember that nu of x, where nu, that was the valuation of x, and that was the power of p, which you extracted from the quotient a over b, where x is a over b. And then if you then if you write x like this, but then you and if you in addition require the coefficient xk to be between 0 and p minus 1, then this is actually unique. One thing is that you can write it like this, but it is also unique, and this is called the canonical form of the p-adic number x. Now, we have already seen that any series like this, it does define a p-adic number. To show that all p-adic numbers can be written like this, all we have to do is to show that if you look at all expressions of this form, they are actually, they form a complete set in QP. So let's look at that. Well, first of all, yeah, so we first of all observe that series of the form we had there. They form a field because we can add them, multiply them, and divide them in a natural way, like we do with the series. And we can also subtract one series from another, and that's a special thing we have to say a little bit more about later. Because what is not obvious, let me go back here a little bit. When you see something like this, all terms are actually positive rational numbers. So each term is a positive rational number. So how can this represent a negative number? And that's something which we will get back to, which we'll show later. But anyway, this shows that if you look at the set of series of this form, they can be added, they can be multiplied, and they can be and you can subtract one series from the other. So it has all the operations which you need to define a field. So they do form a field, and since they converge, they constitute a subfield of QP. So to show that it is all of QP, we only need to show that it is complete. Okay. So to do that, we show. So we take a Cauchy sequence of series of this form. So each xn is a member of that Cauchy sequence, but each xn is of the form some digit akn between 0 and p minus 1 times p to the k. So each term in the sequence is an infinite series. Okay, so that's each term. Now, since this is a Cauchy sequence, then the p-adic difference between two of them can be made as small as we wish by just choosing n1 and n2 large enough. So more precisely, given any m, we can make the p-adic difference between the two sequences x, between the two p-adic numbers xn1 and xn2 we can make that p-adic difference to be less than anything we wish. So for any given m, little m, we can make it less than p to the minus n. But and this so since it's Cauchy, we can find a natural number capital N such that this holds for all indices n1 and n2 larger than capital N. But now think about it. What does it mean for two p-adic numbers to be less than p to the minus n? It means that all coefficients with index less than m, they're equal, right? Because, you know, so this also means that if you fix a k and let n vary, so I mean, if you look at these akn's here, where k denotes the position in the p-adic series, and n denotes its membership in the Cauchy sequence. If you fix a k and then let n vary, and since you have this, that means that if you fix k, then this series akn is eventually constant in n. So that means, in particular, that the limit of akn for a fixed k exists. And so if we call that limit ak, and then it's easy to show that this expression here, but first of all, it gives you, so this ak will also be a number between 0 and p minus 1. So this series converges, and it will be the limit of this Cauchy sequence. So what do we have then? Well, we started to say.
Sorry, Tom. There is a question.
Yeah.
Push the button. Push the button.
Yeah.
And all the time or just one? All the time. Can you hear me?
I can hear, but with some difficulty. With some difficulty. Yeah.
Can you hear me? No.
Yeah. Sorry.
Maybe it's easier if you say it.
Yeah. I can hear. I could hear you talking, but okay. Go ahead and see how it goes.
Okay. So you say that the field that you're working with is a subfield of QP, and you mentioned that if you prove that is complete, that's enough to prove that is the whole QP, correct?
Yeah.
But how do you know that that subfield is just a closed subfield of QP and it's not the complete QP?
Yeah, I'm not quite sure if I got everything there, but let me just say again what I said. First of all, QP is the completion of the rational numbers under the p-adic norm. So whenever I have a sequence of p-adic numbers which converge in the p-adic norm, then that limit will be a member of QP, right? But also, if I can show that the set of those series, or let me go back, yeah. If I can show that the set of these elements is complete, okay, and it is a subfield of QP, why can I say that it is equal to QP? Well, that is because QP is by construction the smallest field which contains the rational numbers as a dense subfield. Okay. Now these series here, they do contain the rational numbers. Okay, and yeah. So just to say it again, QP is by construction the smallest field, which contains the rational numbers as a subfield. The set of expressions of this form, they form a field, and they contain the rational numbers, and it is complete. And since QP is the smallest field with that number, then it must be equal to it. Well, okay. First of all, this field here, the set of these, they are a subfield of QP, and since are complete, then there must be all of it. I don't know. Did that answer your questions, or do you still have doubts?
Yes, the smallest field was the key fact that I needed. Thanks.
Okay. Thank you. Okay. So let's see. Yes. Yeah, so that's that. Okay, so let me say this thing about negative numbers. It looks strange, you know, that since every term in this infinite series they actually consist of positive rational numbers. How can they produce a negative number? And that has to do with simply the feature of this system, namely that we can show that for any p, if you look at this series, it actually gives you the number, gives you the rational number -1. And that's because you can go like this. You can take this p minus 1 outside. Well, first of all, this series converges. That's the one thing. And then this series here, this is a geometric series. And the factor there is p, but the norm of that factor is 1 over p. So it actually converges in QP. And then we can use the usual formula for a convergent geometric series. So p minus 1 was already outside the sum. And then the usual formula for a convergent geometric series with factor p is simply this, and then gives you -1. And everything here is okay to do because this is a convergent series. So we are allowed to do this within the p-adic numbers. So this is a straight. So this shows that at least -1 is in there, but then more generally, if you take any p-adic number with all this like this, and then if you look at this series where bk is defined like this, then that will be equal to -a. Then if you take this series and you add this series with bk defined like this, then you get 0. And that's a strange thing because you have the sum of two series. Each of them have terms which are strictly positive, and they give you 0. Now that means that we don't have a linear order for QP like we have for the reals or for the rationals. So I mean, this distinction between negative and positive does not exist in the same way as it does for the. So here, this thing about the negative has nothing to do with order. It's just an algebraic feature. Okay, and now we come to the next topic. So what we will end up showing is a QP with the topology, or with the metric we have defined, that it is actually, we want to show that it is a locally compact, totally disconnected group. So let's look at the totally disconnectedness first. Now I changed the notation for balls a little bit. I say that B sub k of A is those p-adic numbers which have distance less than p to the k from A. So and the reason I write it like this is that the only numbers which can appear as values for distance, they are on the form p to the k, because that's the range of this norm or the p-adic norm. Okay, so and so that is the closed ball with center at A and with distance less than or equal to p to the k from A. And then I say bk upper O or A to be the open ball, namely the set of x which have p-adic distance less than p to strictly less than p to the k from A. And now the funny thing is that since our absolute value only assumes discrete values, p to the k, then that means that the open ball with radius p to the k is actually equal to the closed ball with radius p to the k minus 1. So it means that every closed ball is also an open ball, and vice versa. Every open ball is also a closed ball. So in particular, all balls are both open and closed, and since they are used to define the topology of QP, it follows that QP is a totally disconnected metric space. Okay. And yeah, and another thing we need to observe is that the balls BK0, that means that with k less or equal to 1. That means that the balls, the balls with center at the origin, 0, and which have distance less than or equal to 1 from 0. Okay, let me rephrase that. So the balls with center at 0, they are additive subgroups of QP, and that again has to do with the non-Archimedean property, namely that if you take two things which have this less than r to 0, then the sum will also have a distance less than r to 0 because of the non-Archimedean property. And if in addition k is less than or equal to 0, that means that the distance is less than or equal to 1. These are not only subgroups, but they are subrings of QP. And that is because, the absolute value has the property that the absolute value of a product is equal to the product of absolute values. And if each of them is less than or equal to 1, then also the product has value less than or equal to 1. Now, there's one special one about these balls, which in my notation then would be B sub 0 of 0. And that are those which are distance less than or equal to 1 from the origin. And they have a special name. They're called Z sub P. And the Z there is used because they are called the p-adic integers. And the reason they are called integers, which I'll get to soon, but first of all, so that very special ball, which is also a subring, they are the ones which are distance less than or equal to 1 from the origin. It is it is compact because it is a ball, and it's a subring because k is less than or equal to 1. And so what can we say about this? Well, in fact, if you look at what this means, what does something from ZP look like? Well, let me go back a little bit. It is a series like this, or like this, where this nu of x is larger than or equal to 0. That means that all these powers of p, they are larger than larger than or equal to 0. And if you cut that series off after finitely many terms, then you get a rational number. And any rational number can be rational number, that's one thing, but any positive integers can be written like this with only finitely many terms, and where this nu of x is larger than or equal to 0. So that means that since this finite series are dense in the set of all series of this form, it means that the positive integers are actually dense in ZT. And since the positive integers are Z, then so are Z itself, the ring of rational integers. Because if you think about how the norm was defined, everything in Z has norm less than or equal to 1, because there's no denominator. Okay. Let's see. I think I would like to take a 10-minute break there, and we start again at let's see, at 7 p.m. my time. That will be at noon your time, right? But before the break, if there still are any questions, let's do that, and then we meet again at noon.
Okay. So we have a 10-minute break. Am I right, Tom?
Yeah.
You said that you want to take a break, a 10-minute break.
Yeah.
Okay, perfect. Are there questions for the speaker? Okay, so in 10 minutes, we come back. Okay?
Yeah, okay. Yeah. So we start again at noon. Okay.
Guys, one important thing, all the materials for the school are available in the page. All the materials for the school are available on the webpage of the conference. For instance, the presentation of Professor Ligueras is already available. In addition, if you have comments or questions, there are many experts in periodic analysis. For instance, you can contact Mr. Brian Zambrano here, or you can contact me if you have specific questions about problems, concepts, etc. Okay, guys, you have 10 minutes.
And I want to say something also. Remember that the visitor pass that they give you today in the entrance, you have to return it later when you go away. Okay.
Hay muchos. Yo le pregunta como muy abierta. No, es muy complicado la interacción y además tenemos problemas. Para que ahora escucharse. Es más fácil si habla con acá. A lo que pasa es que la educación es un poco diferente. No es la misma. No, porque para él sí, el aula es no, aquí la educación es cerrada. Es por eso. Sí, las bolas son abiertas cerradas. Colocar menor que 3K o igual menor que 3K es lo mismo. ¿Por qué? Porque las potencias de P forman un contado discreto. Sí, pero son de... No, es la misma. O sea, las bolas la bola con centro es A, el radio R la define como los puntos de distancia a A, que es menor o igual que P a la G. Esa es la notación.
Por ejemplo, esa es la notación que tiene.
Exactamente.
Y la que en la música nos dieron es menor.
Menor es
sí.
No, pero en el artículo es
nosotros nos dieron
sí, pero si uno dice que es un tallo, no importa si usted coloca menor, de todos modos va a conseguir una potencia, es un tallo, muéstremelo para cuál. Sí, dale. Entonces es un tallo. No, pero esto es no, pero esto es un contexto diferente. Este no son los reales. Un campo, o sea, es un campo. Entonces, en un campo general, si lo hay menor y menor. En un campo general, pero no se imagino que pero
Una mesita esta la puedo después mover para mi copia para poner las notas ahí, pero después. ¿Está llevando el tiempo? Sí, faltan dos bases. ¿Faltan dos? Sí.
También tengo. Hacerle falta. Me vas a ver y vas a salir corriendo.
Ya vamos a retomar. Ya vamos a retomar. Okay, guys, let's
continue.
Okay, let's start again. Are you ready? I have to say, yeah.
Okay, guys, let's continue with the course.
Yeah.
Please, proceed.
Yeah, thanks. I would say it's too bad this thing with the sound because I can hear you, but it's very distorted. Well, I hope you can hear me, but at least if you don't, you can at least read the slides. Anyway, when I tested this on Friday with Manuel, everything worked beautifully. So I don't know what happened. Anyway, let's continue. And we just defined the p-adic integers as well as the p-adic normal is equal to 1. And we noted that the usual integers as well as both the positive ones already are dense, and hence the set of all of them are dense. So now let's look at local compactness. So if you look at the set P times Cp, that's the ball of elements which have a distance less than p to the minus 1 from the origin. So if you look at the standard form again, they are the ones where, which start which start with p to the power 1 or higher powers. That means that the quotient between Zp and p to Zp is isomorphic to the set of x zeros, which vary from 0 to p minus 1. And by the way, the operations here are defined. These then are the finite field with p elements. So the quotient so the quotient between Zp and p times Cp is the cyclic group with p elements, and they also constitute the finite field with p elements. But here we only need the fact that they are the cyclic group with p elements. And as such, it follows that Cp itself is the disjoint union of p cosets or p times Cp. You know, you have p times Cp plus 1, p times Cp plus 2, etc. up to p minus 1 plus p times Cp. That's p cosets. And that gives you everything in Cp. And so Cp itself is the union of p cosets, each of which is a ball of radius p to the minus 1. So that is the first observation. And then more generally, if you take any any two natural numbers m and n, you have that every ball BMA, that means every ball with the distance less than p to the m from A is the disjoint union of p of m minus n balls of radius p to the n. So that is an argument similar to the ones we did up here, only a little bit more complicated since we have different radii. But what does this mean? You know, so this ball BMOA, so that's any ball in QP. Any ball in QP can be covered by finitely many balls of arbitrarily small radius, namely p to minus n. You can let's see, did I get those in the wrong order here? Anyway, let's see. Those balls which constitute BM or A is the union of p m minus n balls or radius p to the n, and that p to the n you can make as small as you want. Right. So this n could be any negative number as small as you want. So it means that all the balls, they are actually totally bounded and hence compact. And since they constitute the basis for our topology, then that shows that QP is a locally compact space as a topological space. And from before we have that it's totally disconnected, and we know that it is a group. Well, it's a totally disconnected locally compact group. And when I say a group here, I mean QP as an additive group under addition. So QP is a totally disconnected locally compact group under addition. Yeah. So let me just, I think I said it a little bit wrong, but anyway, if you take any ball, you can write it as a disunion of p to the minus n minus n balls, each of which has radius p to the n. And this n you can you make as negative as you want, so the radius can be as small as you want, and that means that each ball is totally bounded. And since you are in a complete metric space, that means that each ball is actually compact. There you are. Now we're going to talk about characters and the dual group of the locally compact abelian group QP under addition. So the dual group, or any locally compact abelian group, that consists of the set of characters, which means homomorphism from the group into the unit circle, which are continuous. So we start by defining what we call the basic character, chi sub 1. We define it as the exponential of 2 pi I, and then we take the fractional part of x, and the fractional part of x means that part which is to the left of the comma, so to speak. I mean, it is the part of x which has negative powers of p in it. So if x is 0, or if x is equal to the element 0, or if it has norm less than or equal to 1, then that the part is then that fractional part is 0. And if it has norm larger than 1, then it is it is this sum here. Yeah. So just to say it simply, it is the part of x which consists of the negative powers of p in the standard form of x. Okay. Yeah. And so that was one particular character which we call chi sub 1, and then when we have defined chi sub 1, we can, for any element y in QP, define another character which we call chi sub y, which is defined simply to be chi sub 1 of y times x. So for each y in xp, you get a new character this way. And the claim is that these are all the characters. Namely, if you look at all the continuous characters of QP as an additive group, then these characters which you obtain this way, they give you all the characters. And not only that, but this assignment, which takes an element for QP to the character which we have denoted by chi sub y, is some isomorphism between the locally compact additive group QP and its Pontryagin dual group. And the Pontryagin dual group, as you may not know, that consists of the continuous characters of your group with the compact open topology. That means it is the topology of uniform convergence on compacta. So let's see if we can. So here's the theorem. So this assignment, which we mentioned, y goes to chi sub y, is a topological group isomorphism between a locally compact entity group QP and its Pontryagin dual. Yeah, and I already said what the Pontryagin dual is. And yeah. So the compact open topology is the topology of characters described by uniform convergence on compact subsets of QP. I'm not going to give the full proof of this theorem because it's a bit technical, but I would like to just mention the first step, which is sometimes presented as in a sort of awkward way, but there is one good way to do it, and namely to say that the first step is to say that if you have a continuous character on QP, there is an integer such that this character is constantly equal to 1, or it is trivial of the ball of radius p to the k with center at 0. And the proof for this is simply that since chi is continuous, there is an integer k such that chi maps this ball b sub k 0. That means the ball of radius p to the k about the origin. It maps that into the neighborhood, which are called U here, consisting of those Z in the circle group, which have distance less than 1 from 1. And what does that mean? What does it mean for something to be in this neighborhood U? Well, these are the points of the unit circle, which make an angle less than 45 degree with the x-axis, or less than the p-quarter. Okay, so if you can see it before you, it's yeah. So there are the complex numbers of norm less than with norm equal to 1, which make an angle less than 45 plus minus 45 degrees with the x-axis. Okay. But also, you know that BK0 is a subgroup of QP. So its image under chi is a subgroup of T, because chi is a homomorphism. But the only subgroup of the unit circle, which is contained in this set, which makes an angle of 45 degrees or less with the x-axis. The only subgroup which has that property is the trivial subgroup of T, namely the one which consists of the number 1 alone, because any other subgroup of T, they spread evenly out on the unit circle. Okay. So with that done, so this is a special case of the next theorem, or next lemma, I should say, where this is actually much more technical, but it has the same basic idea, and which says that if you have any chi with the property that it is non-trivial on p to the minus 1, and it is equal to 1 at 1, then you can actually write it this way, that is, its value at p to the minus m can be written like this. Namely, that you can find coefficients a0 in the range from 1 to p minus 1, a0 there, and ak in the range between 0 and p minus 1, such that this holds. And so what does this say? Well, it says what chi is on p to the minus m. But the thing is that any character is actually uniquely decided by what it does to the powers of p. So if you know chi's value on the powers of p, then you know it everywhere. Okay, that's because of this that anything in QP can be written in this way, which we talked about. Okay, and so this is the last step in the proof, and then one checks that yeah, so the fact that the assignment y goes to chi sub I is a group isomorphism. Okay, so it is clearly it is a one-to-one homomorphism into Q p hat, and what we just showed in the previous sum is that everything in Q p hat is of this form. That there is a Q sub y equal to it, and then finally one has to show that not only is it a group isomorphism, but it also is a homeomorphism with QP with this normal usual topology, and the QP hat is equipped with the compact open topology. So that is the last part of that. Yeah. Okay, so now let's see that I may not need my full 2 hours here. So Wilson, maybe you, I don't know how to do, but at this point, I would like to just give some examples and some easy ones. And they are taken from, there's a book by Gouveia, which is used very much in this in the context of p-adic numbers. And I just would like to comment on a couple of his examples. So, for instance, just to get a feeling for why this idea about p-adic numbers arose, is that what people were trying to do is that, you know, you start with a polynomial with integers coefficients, and you want to find out if the equation p of x equal to 0 has any integers solutions. Then one method is to find all solutions of this equation, and first mod pi 1, then mod pi 2, then mod pi to n, and do this for all n. And so that is one way to handle this question. And then what you can what then will happen is the following. So if you do this process, we can have the following outcomes. It could be that we get the contradiction after a finite number of steps, and that means that there is no solution. And it could be that the process stops after n steps, and well, it stops means that x is equal to 0 for I larger than a certain n, and then we take that xn. That xn will then be a solution. But it can also be that the process continues indefinitely. And then there are two possibilities. If you don't have any contradiction, then you still have a solution. But it could be that this infinite series, which you then get, it could be that it actually, represents a rational integers, and then we also have a solution in that case, and we have a solution as an ordinary rational integers. But it could be that this series does not find an ordinary rational integers, but something in ZP instead, which is not a rational number. And then we have a solution which is p-adic integers, but not a rational one, and it will not be it will not be a real number either. So to get an idea how, so this may be thought of as maybe part of the background why Hensel thought about introducing the p-adic numbers. You know, trying to solve an equation modulo all powers of a certain prime number p, and then you get something, and you get one of these cases, and you try to make sense of it. And it's especially what he would like to do was to make sense of that second possibility in number 3, namely that we have a p-adic integer here, which is not a rational one. Okay. Oh, by the way, I should mention that anything like this will be a rational number if and only if, after a certain index j or I, that the xi's they repeat themselves, or there is a pattern. Okay, after a certain number. Okay. So let's see, how would we go about doing this for, let's say, the equation x squared equal to 21. And let's take p equal to 3. And of course, here we know what the solutions are, namely x is plus or minus 1. But let's pretend we didn't know this, and we try to solve this by the method which we indicated here, by this method here, with p equal to 3, and see what we get. Now, since we here know that that x equal to plus or minus 1 is a solution, that number x plus or minus 1 will also be a solution for all the congruences for all n's, for all p to the n's. So we can use that and see what happens. So if we first take the solution x equal to 5, and we put it okay, so then we see what happens if we take the equation or the congruence 3 to the power 1, then 5 is equal to 2, so that's our first approximation, so to speak. And then we go to the next one and we get 2 plus 3, and then we go to the next one and get 2 plus 3 there also, and it stops there. It doesn't give any more. So nothing changes after this, and we get the triadic expansion of x equal 5, which is 2 plus 1 times 3. And if we didn't know that 5 was a solution, the method of doing this was that, you know, for, let's say, for to solve this first one, we will simply put in x equal to 0, 1, and 2, and see that we had solution for x equal to 1, x equal to 2. So we had 2 solutions. For the next one, we would know that the solution mod 9 would also have to be a solution mod 3 if it is if we take its modulo with 3. And that means that in the second equation here, we can look for a solution of 2 plus 3k and put it in, and then we find a k which solves this one. And so we go on and on. But here we don't have to do that because we know what we are supposed to get. But it gets slightly more interesting if you take the other solution, minus 5. Minus 5 corresponds to 1 in mod 3. And then at the next attempt, we can use that method which I just mentioned. Namely, we look for a solution of the form 1 plus 3k, square it, and put it into the congruence x squared equal to 5 modulo 9. Excuse me, x squared equal to 25 modulo 9, and put it in there, and look for a solution of the form 1 plus 3k, and you will get that that you can take k equal to 1, and that gives you 1 plus 3. And so you go on, and you know that for the next congruence, 3 to the power 3, you know that your solution here must be of the form what you had here plus a multiple of 9, and you put it in, square it, and you solve for that multiple, and so you go on. So if you do that, but I don't have to do all this because I know what I'm supposed to get. And so we get successively something like this. And then after a while, you convince yourself that what you get here is something which goes like this, that after the power 3 squared, so you get 1 plus 1 times 3 plus 2 times 3 squared plus 2 times 3 to the power 3, etc. And then you show by induction that after this point here, everything is of the form 2 times 3 to the k, power k. So if you use this method, you get this solution here. And this then is supposed to give us -5. So let's check that. Well, let's see, 4 plus 3. So this is, once again, this is a geometric series with factor, so we start with k equal to 2, so we factor that one out, and then we're left with the series start with 0, and then, so once again, so this is 4 times 18, 2 times 9, and this is a geometric series with factor 3, so there's 1 over 1 minus 3, and lo and behold, that gives you -5. That's it. And of course, this is a silly way of doing it, but it is just to explain or to illustrate how this method works. Now here we knew what the solution was, but this method can be used in any context. So sometimes you end up with a p-adic number which is not a rational number, and things like that. Okay, and here is an even more silly example, but this is also meant just as an illustration how p-adic numbers can be used. This is also taken from the book of Gouveia. So let us look at this equation here, 1 plus 3x equal to x, and solve it, right? Now we see right away that the solution there is x is equal to -1/2, right? But let's say that we did not see that. And what we can think of is that the left-hand side, that is something which we call f of x, and we are looking for fixed points for that function. So we have a function x, and we try to find an x such that f of x is equal to x. And that is a classical fixed point problem. And when are we guaranteed that we have a solution of that type? Okay, that means that is in the following case. If you have a complete metric space, and if on that space you have a mapping, which is also a contraction, then you are guaranteed that you will find a fixed point by iterating your function, starting with any value, and just use f of x on that starting value infinitely many times, and you get a fixed point. So let's do it this way. So let's first make sure. So let's do it in Q3. So let's first make sure that that this f is a contraction. So f of y minus f of x in Q3 is equal to this. And the norm of 3 goes outside, but the 3 norm of 3 is actually 1 over 3. So this is a contraction with factor 1 over 3. So it does have a fixed point. So then general theory says, okay, start with any point you like, for example, x0 equal to 1, and then use f on that point again and again and again. So you start with f of 1, and then you get something, call it x1, and then you take f of x1, and you get x2, etc. So we have this pattern here. And so here is the pattern. You start with this one, and you use f for x0, that is, by definition, f equal to this, and you just compute it, and then it goes on. Actually, this should be x1 there. This is a misprint. This should be 1 plus 3x1, and that gives you this one. In general, xn is equal to this finite sum there. And again, it seems like you get the geometric series. So after infinitely many steps, we get the geometric series. Seems like with factor 3. And that should give us -1/2. And that's what we got. And of course, this is just an illustration. This is not the way we normally would have solved that equation, but just to illustrate how p-adic numbers work. So I think I'll stop there. And yeah, so thank you. And if you have questions, I can take them now. Thank you.
Thank you very much, Tom.
Thank you.
Do you have questions or comments for the speaker? Good. So let's take a break, the lunch break. We are supposed to come back to 3 p.m. Mexican local time. Okay? So see you at 3 p.m.
Yeah.
Bye-bye.
Okay, bye-bye.
Okay. We have to stop the recording.
Yeah. I think maybe everyone can do that. So maybe I can do it. Okay.
Yeah, ready.
So just a reminder, you got the coupon for the meal, right? For the lunch. It's right there, in the terrace, right? This level, just go in. And you can go anytime between 1 and 3.
Okay.
Yeah. I don't want to. It's now. But the metal wasn't in there, so the thing is. Mira, you can ask you this. Yeah, I choose one. Yes, so for example, the internal is this true? So you're looking for the x, that is x0. We need to find all the x in n. Okay, so the first one is now. Okay. That's what it's being about the no, we need to this doesn't have solution in 6, so it's 2. This doesn't have solution in 2. Okay, so this doesn't have a solution? Yes, 1. So x0 also. So you're using more piece. The cube is not the 0. It has a solution. X0 also. I mean, one. So you have to. Well, take one. Take X0. Okay. So second thing is now you need to take more time. So you have to solve the different x0 plus x1 is and this has to be 0. So you can solve. Well, that's the one. It's like a hypothesis to make sure that and you need to. If you're inside a they might get you. I don't know whether this function is inside. But if you can grab one for inside a and you play you're gonna get one. can you go with a program that you already know that doesn't have to be sensitive?
El señor dijo que se las entregáramos ahí, pero y tú vas a salir por acá arriba y en tu caso, pues no sé.
Well, I mean, the method is a method of reasoning. Enhances lemma gives you the hypothesis that you need to make sure that you have because Perdóname. You can come there, you know. Yeah, well, it has a lemma is giving you this hypothesis to make sure that this is relevant. I didn't check the hypothesis of the lemma, so I'm not really sure if this is lemma. Got it. Maybe it does. Well, what were the solution? The hypothesis. Was, I mean, the method is always the same. Henson's lemma is really just shoot. Oh, yes, the help X0 is yeah, and you can follow the algorithm. If you're asking for a easy number, I don't know. I don't know. I didn't have easy number. Oh, you're right. Exactly. Like something easy to write down. I don't know. I don't know any number, but maybe you know. Yeah, you can. Yeah, you can see. Sorry, I give you.
That's what she was trying to say. She was trying to sorry, where are you?
I don't know.
Oh, you are. Where is your? Oh, that's how. Yeah. Your name?
Yeah, yo solo subí todos los dos.
Oh,
Excepto uno que pone tamaño. Mamita al revés.
I guess
Al ver ahí.
well, I guess everybody just in case.
No hay ni siquiera el que hay. Sí, ¿lo viste? ¿Lo viste mal? Porque quizás es convexidad, es al revés. Prisas, simplemente convexidad, ¿no? Convexa. Y alfa menos uno, pero alfa mayor que una convexa. Vos pensás convexidad, pensás que el mundo por arriba, el sistema. Capaz que estoy mal, y por eso no me sale. Es. También es mayor. O antes salió como un. Por lo que recuerdo, sí es un. Sí, sí es. Entonces, así no. Pero por eso también es complejidad, sale. Sí, tiene que ser. Pero ni al revés. Sí.
Oh, gracias. No, ya me traje dos. Yo voy a estar la mayor parte del tiempo aquí en la pizarra. A veces voy a bajar por mis notas y voy a moverme en esta área. La que ustedes vean que es más conveniente.
Él es el que está adelante. A ver. Como para poner la computadora mantener el micrófono. El micrófono. Tiene la ¿Ya tenemos abierto el Zoom también? Sí, ya está.
Sí, se ve bien. Bueno, yo tengo las gafas de ver de cerca. Entonces yo... Pero esto se va a pagar, ¿no? Ya no vamos a ver este cuando sea Welcome to Guanajuato, sí.
Ajá. Aquí que va a haber entonces.
No, ya voy a escribir en la pizarra.
Okay, entonces, ¿quiere que se apague?
Sí, porque voy a escribir en la pizarra. Tal vez al final necesite presentar un PDF, pero solo al final.
Sí se puede, nada más.
No, le avisamos.
Para que Gracias, Manuel.
Oye, Manuel, es importante que le des una mirada al tamaño de la letra y si puedo escribir toda la pizarra, pero desde la computadora, ¿no? ¿Ah, sí? Ah, perfecto. Déjame. Se ve hasta este, a ver, se ve hasta acá. Ah, oye, y esto tiene, déjame mirar, esto se sube, ¿no?
Tienes como tres. Está del medio. Está pintando en el fondo. Las pizarras.
A ver,
Que también puedes hacerlo, no digo que no, pero las pizarras son.
A ver, comienzo con esta.
Y aquí hay otra.
Aquí hay otra.
Es que es mejor hacerlo por el centro, si no la ves como. A ver, pero es que a lo mejor esa es la de arriba, que es la que hay que seleccionar. No.
No.
La frase está en la entrada. La verdad, no sé cómo funciona,
¿No tiene un control?
No, porque todo es.
A ver, cuidado la mano. No. Sí, tiene un problema esto. Yes, it's time. Go ahead.
Okay. Okay, so welcome back. Welcome back to the school. Let's resume with the second session of the course on Introduction to Periodic Analysis. This session will be given by Professor Wilson Zúñiga from Cimpa and the University of
Texas.
Rio
Grande Valley.
And please.
Okay. Good afternoon, everyone. Can you hear me?
Yeah.
I think that it's not necessary to thank to the organizers for inviting me. I'm going to use the whiteboard. You have access, you have a printed copy of one survey paper about periodic analysis. I don't have time to provide or to go through all the details presented in the paper. I just want to present some general ideas about periodic analysis. Today, we are supposed to cover up to integration because tomorrow you need integration for the coming course. So let me begin by reviewing some ideas presented this morning by Professor Diegues. So let P be a prime, a fixed prime. So if X is a non-zero rational number, this symbol means Q minus the origin. Then, by using the fundamental theorem of arithmetic, X can be represented in a unique form as a power of P times a fraction, where A and B are not divisible by P. Then, this exponent, gamma, is an integer. This integer R is unitely, R or gamma, R is unitely determined by X and P. The periodic absolute value of X is defined in this way: P to the minus R if X is different from 0, or 0 if X is 0. Okay? It is not difficult, this is just an exercise, to check that this function defines a norm on the field of rational numbers. So this means that the absolute value of P is greater or equal than 0, and the absolute value is 0 if and only if X is 0. The second condition is the absolute value, or this absolute value, is a multiplicative function. And this assertion is valid for any X, Y in Q. And finally, we have that the absolute value of X plus Y is less than or equal to the max between the absolute value of X and the absolute value of Y. Okay? This last property implies, property 3, implies the triangle inequality. But the converse is not true. Now, with this norm, we define a distance. I'm going to put the definition here. The distance between X and Y is by definition the norm of X minus Y. And then Q with this I'm going to use this symbol to mean the metric space associated with this distance. Okay? So it's a metric space. Now, the completion of this metric space is the field of p-adic numbers. Okay? Now, any p-adic number different from 0 can be represented as a power of series of this form. P to the R, now we have a series, I from 0 to infinity, xi, pi. These numbers, xi, are p-adic digits. This means that these numbers xi belongs to this set. Okay? In addition, we need this condition x0 must be different from 0. So this number, this integer, is unitely defined. Now, with this notation, let me use a different color. I want to write here.
Wilson, can we ask you to increase the size of your writing, please?
Okay, yeah, I'm gonna do that. Okay, so I'm gonna increase the size. The writing. Okay. So the absolute value of x is p to the minus r. Okay. Notice that here in this representation r here there is a positive sign here, but if we want to compute the p-adic norm, we have to put minus r. Okay. Now, there is an important operation called truncation. I'm going to continue here. Truncation. Also called mod. The reduction modulo p to the n plus 1. So truncation means that we consider only a finite number of digits in the p-adic representation of x. For instance, if x has an expansion of this form, then plus 1, we consider only, we consider only a finite number of p-adic digits. Here, we have to put an element belonging to Zp. Zp is the set of p-adic numbers satisfying that the p-adic norm of x is less or equal to 1, or is the set of series of the form and so on. Notice that in this expansion, there are no negative powers of p. So all these elements are the elements of Zp. Zp is the unit ball. The unit ball. The unit ball is also a ring. Zp with the addition and multiplication is a ring. Okay. Now, I'm going to continue here. This is the unit ball. If we multiply the unit ball by a power of p, then this operation, get another color. This operation is called a dilation, and this dilation, this operation changes the radius of the unit ball to p to the minus n. Okay, so if we start with the unit ball and we multiply the unit ball by a convening power of p, we change the radius of the unit ball. Now, if, let me use another quote. If we perform a translation, this is a translation, then we get a ball. This is a ball with center at A, radius minus n, which is the set of elements in QP, such that the distance between x and A is less than or equal to p to the minus n. Okay?
So the radius is p minus p minus.
Here, minus n.
P minus. You mean the radius?
No, but the convention that we are using is we put just the exponent. But here, if you use the norm, you have a negative sign. If you use this notation, this is the ideal notation, you have to change sign. Okay, let me see, yes. Now,
Which value is the blue instead of the green?
okay, no problem. I'm going to continue with that. Now, I have to use this. Let me erase this. Now, the unit ball is a disjoint union. This is the symbol for the disjoint union of balls of this type, A plus PZP, where A runs from 0 to P minus 1. If we take an element in CP, then this X can be represented in this form, X0 plus X1 P, X2 P squared, and so on. We can rewrite this number in this form, P, and here we get an element of this form, 1, X2, P, and so on. Notice that this is an element of the unit ball. So X can be written as X0 plus PCP. This notation means that if we consider only one digit, then there is just one diagonal, X0. In this way, we establish this identity. Okay? Now, in other words, the unit ball is a disjoint union of P balls of radius P to the minus 1. Now, let us consider a ball of this form. This is the center. The radius is P to the minus 1. This ball can be written as a disjoint union of this form. Now, the center is X0, X1P, and then P squared CP. Now, this is the center, and let's say this is the radius. So the meaning of this assertion is that this ball is a disjoint union of P balls of radius p to the minus 2. The point is that we can continue this construction up to infinity. And the conclusion is basically that Cp is a prime. Now I have to go back to Edwin, can I use a smaller phone?
That one was okay. I mean, but the previous one was okay also, because we have a little zoom in with the camera, so it's okay.
Okay. Okay, this is an important fact. The balls are open and compact. Open and closed, sorry. This is a very, very particular property. Okay. Let us consider a ball with radius p to the minus n. This is the center. Okay. So this ball can be written in this way. Now, suppose that we are interested. Oh, this is open and closed. Then the complement of this ball is also open and closed. This ball is open and closed. Now, if we want to find the boundary, I'm going to use the symbol for the boundary of the ball. We have to remember that the boundary is defined as the topological closure of the set minus, now we take the complement of the set, and this part denotes, again, the topological closure. Now, using these facts, we have that this is the ball with center in A, and this is this set. In conclusion, the boundary, I'm going to continue here, the boundary of this ball is the empty set. Okay? The boundary is not the sphere with center at A and radius p to the A. In other words, this is the set of points in QP such that the distance between X and A is exactly p to the minus A. Okay? This is important. Okay? So the topology of the periodic numbers is completely different to the topology of the set of real numbers. Now, I need some observations about QPN. Right here, QPN. We can extend the periodic norm to QPN. If X is a vector in QPN, we define the norm of X as the maximum over the I over the periodic norm of Xi. Okay? If we define the order of the vector as the minimum over the i's of the order of Xi, then X, which is a vector, can be written as a power of p times another vector, but this vector satisfies this condition. The norm of this vector is exactly 1. Okay? Sure.
Yeah, Jose is asking to know the minus sign in his definition of the boundary via an intersection.
No. This is important. Okay, no.
No,
This is the right. If we want to compute the periodic norm.
Wilson, I guess he's talking about the sign in the definition of the boundary. You are taking out
below. I think he's asking about the set minus sign in this definition.
This minus.
Yes.
This is the definition. This is the classical definition for the boundary of a set in standard topology. Yes. Intersection. Yeah. Thank you. Yeah, I got it. Yeah.
That will be empty.
Intersection. Yeah. Is the intersection. Thank you. Is the intersection. Yes. Is the intersection. Thank you. Okay. Oh, now let me mention something. The norm is p to the minus the order of x. Okay. Okay, now the n-dimensional, this is the notation for the n-dimensional, this is the dimension. This is the radius. This is the center. Is the set of points in QPN such that the distance from x to a is less than or equal to p to the r. We can write this set in this form A, the unit volt. Now the n-dimensional unit volt, p to the minus r. Okay. Now we have also this set. This is the n-dimensional sphere, radius p to the r. The center is A, and this is the set of points in QPN satisfying that the distance from x to a is exactly p to the r. This is a sphere, the n-dimensional sphere with center in A and radius p to the r. Okay. This is just a review of the ideas presented by Professor De Gernes this morning. Okay, now I need a definition, right here, definition. A topological group I'm using the multiplicative notation. A topological group is a topological space that is also a group such that the group operations are continuous functions. This means that there are two group operations, the multiplication this function, this must be continuous in the product topology. The second operation is the inversion, which is a function when g into g, given x, the image is x inverse. Okay? This function must be also a continuous function. Okay, we say that g is locally compact. It's locally compact if every point, let's say G in G, has a compact neighborhood. Okay. Now let us consider QPN with the periodic norm. This is a metric space. And then this is a topological space. But QP, oh, of course, the distance here, let me write the distance. The distance here is given by this formula. Okay. The point is that this space is locally compact. Why? Because given a point A, the ball with center in this point and radius p to the n, this ball is compact. This is compact. Then this is a compact neighborhood of an arbitrary point in this space. So this space is locally compact. Okay.
Sorry.
Yes, go ahead.
Could you repeat the definition of the local compact? Sorry.
Locally compact means that every point in this space has a compact neighborhood.
The ball.
And in this particular case, this is a locally compact space. Why? Because given any point in QPN, this ball, this is a ball around A, the ball is compact. Let me write here that all the balls are compact. Okay.
Thank you.
Now, associated with QPN, there are two different groups, two different topological groups. Yes.
Very another question. Does Heine-Borel apply?
And yes. Yeah, because this is a metric space. Yes. By Heine-Borel, I mean asset is compact if and only if is closed and bound. Okay, this is true in this frame.
Okay. I think that was it.
And now, associated with QP, we have two different topologies, two different groups. Analytic group, and I'm going to use this notation. This is the standard notation for the element different from zero. QPN with the problem. Of course, these are locally compact spaces. We already mentioned this. Now, let me erase this. The assertion is these two groups are locally compact topological groups. Okay. I'm going to consider the case in which n is 1, dimension 1, and I'm going to consider this multiplicative group. The purpose of the exercise is show that this is a locally compact topological group. Okay. So we have to show the following two assertions. the product is continuous and the inverse is also a continuous function. Here, it is important to remind that the continuity in the metric spaces is completely characterized by sequences. The continuity is completely characterized by sequences. And that causes this A and this B. If we apply this result to A and B, we have to show, I'm going to call it A prime, we have to show the following. If Xn is a sequence converging to X, and Yn is a sequence converging to Y, then the product converges to XY. This is part A, and part B becomes if Xn converges to X, then the inverse of Xn converges to the inverse of X. Of course, in this notation, I'm going to write it here, Xn, X are non-zero periodic numbers. Okay? Let me erase this. Let me recall the following result. We need this information. If Xn converges to X, of course, here the convergence is the convergence in QP, which is, I'm going to call this the convergence in the periodic norm. Then, if this is a convergent sequence, then the sequence is bounded. This is one. Okay? If the sequence is convergent, then the sequence is bounded, where C is a constant. Now, let us consider A prime. So, we have to estimate the distance between Xn, Yn, minus the distance between these two numbers in the periodic norm. Okay? So, we do the following. Notice that this is really 0, Xn minus Xny, Xny. Now we use the triangle inequality. The triangle inequality is valid for this norm. So this norm is less than. I'm going to factor out Xn. And the second term is, I'm going to factor out Y, is Xn minus X. Now we have to remember that the norm is a multiplicative function. So this is really, I'm going to use less than or equal, but really is equal. So is the norm of Xn times the norm of Yn minus Y, then the norm of Y, the norm of Xn minus X. Okay? Okay, let me continue here. Now, we use that we use this property. So the norm of xn is bounded by a constant c. Now, we may assume that this difference, the norm of the difference is very small. I'm going to say that this is epsilon. Then y, the norm of y is a constant, so not y, just. And then we assume that this distance is very small. I'm going to use epsilon. So the conclusion is that the distance, this distance is arbitrarily small. In other words, A prime is valid. Okay? Now for B prime. For B prime, we need the following remark. I'm going to put the remark here. Suppose that xn is a periodic number different from 0 for every n, this is a sequence. And the limit n tends to infinity of this sequence is a number, a periodic number, and this number is a non-zero periodic number. The conclusion is that there is a constant c defined this way. It is the infimum over the n of the absolute value of xn. It is not really difficult to show this assertion. We can do this later. We can discuss this assertion later. But we need this remark for the second part. So for B prime, we have to estimate the distance between 1 divided by xn, 1 divided by x. So if you do the algebra, this is the common denominator. And the numerator. Because xn converges to x, we can assume that this distance is small. This is a constant. Now, we have to use this remark. We need this remark. Yes, why?
Can I put the supreme on there?
Is the infimum. Why the supreme? No, we need the distance to 0.
Is that C the C that you used before? I'm confused with this what C is.
No, I mean, this is. Oh, this is the same C,
Okay,
but it now has a different meaning.
Okay, got it.
Yeah, it's the same constant.
You're
gonna put the C0. Okay,
I
C0.
understood. Perfect.
Okay, C0, and now we put C0 here. Okay. Now, what is the meaning of this assertion? This distance is arbitrarily small. In other words, B prime is true. Go ahead.
Maybe you try to say that C0 is bigger than 0.
Yes, we need exactly that. Oh, yes. Thank you. Yes, I forgot that. Yes, we need exactly this. Yes, thank you. Yes, C0 is bigger than 0. Okay. So B prime is true. Okay. Comments or questions? Let me check the time. Before. Let me erase everything. Oh, no, I cannot use this one. Okay. This is the right one. Okay. This rule, this is an exercise. this group, QPN, with the sum, is a locally compact topological group.
Wilson, that size is.
Oh, the size, sorry. Oh,
Yeah,
okay,
sorry.
so, okay. This is, I'm going to use something. It's a locally compact group.
Thanks.
So, I'm cheating, but okay. So there is a theorem. Let me use a different color. This is the Haar theorem. This theorem says that there is a unique, there is a measure denoted in this way. This is the Haar measure of this group. This measure is unique up to multiplication by a positive constant. Such that the measure that this inequality is true for every non-empty open subset U of QPN, and the measure is invariant in the translation. For any Borel subset E of QP, and for any point X in QP. Okay? Let me try to write here. Okay. So this theorem asserted or asserts basically two things. The first one is that there is a family of distinct subsets of QPN. This family is the so-called Borel sigma of QPN. So there is a family of subsets of QPN. This is the sigma algebra of Borel. Oh my goodness, Borel subsets of QPN. And this family satisfies the following condition. First, the whole space QPN belongs to the family. The second property is that the family is closed under complementation. This means, in other words, if, let's say, if A is a subset in B, then the complement, denoted in this way, AC, also belongs to B. Now, the third property, I'm going to write here, says the following. The family is closed under countable unions. This means, in other words, that if A sub I is an element of B for I in the natural numbers, then this union also belongs to B. We can say that the Borel sigma algebra is the smallest family containing the balls of QPN and satisfying conditions 1, 2, and 3. Okay. This is the first part of the Hart theorem. The second part of the Hart theorem says that there is a function from B with values in the extended real line. I'm using this symbol to denote the extended real line. And this function satisfies the following properties. The measure of the empty set is 0. The second property is for any countable collection, say I is a natural number of pairwise disjoint subsets. Let me continue here. For any countable collection A sub I of pairwise disjoint subsets, it verifies that the measure of the disjoint union of these sets is exactly this measure is this series. Okay. Okay. Some comments about the notation. Let me go back to here. Notation. The Hart measure of A, where A is a Borel set, is denoted as the integral over A with respect to dnx. With this notation, the Hart measure satisfies that this measure is invariant under I'm going to use SC. That the measure of A doesn't change by a translation. In other words, the Hart measure is invariant under the action. I'm going to write here. The Hart measure is invariant, it's too small, is invariant under the action of this group. Okay, we use, this is a convention, we assume we use a Hart measure satisfying this condition This condition says that the volume or the measure of the unit ball of the n-dimensional unit ball is 1. Okay?
Okay, well, that measure is fine.
So far, you don't know that.
So you cannot normalize.
The point is, yes, it is possible to normalize that, but I mean, you need the following result: the measure of a compact subset is 5. Let me tell you something. If you remember the Hart theorem says that the measure is unique up to multiplication by a positive constant. So here we are selecting a particular constant. Okay? Okay, let me check. Okay, let me explain 2 more ideas and then we take a break. Okay, now I'm going to denote by omega, by this notation. This is the characteristic function of the ball of this ball, which is the ball, the n-dimensional ball. This is the red. We have to change the sign. This is and this is the center. Okay. Now, a test function is a linear combination of characteristic functions of balls. So, a test function is a linear combination, let's say, a finite sum of this form. Ci is a complex number, and here we write the characteristic function of a ball. So we have to put an expression of this form. Okay. It is very simple. It's an exercise to verify that this is the space of test function. I mean, this is the set of all possible test functions. D is a C vector space. This is an exercise. Now, the next step is to compute the integral of a test function. Let me right here. Suppose that phi is a test function. The integral of this test function with respect to the Hart measure is, by definition, is the sum. We have to use this expansion. It's the sum from I to L. Ci, the integral. Now, omega okay? But this is just the characteristic function of a ball. So really, this expression is just the sum from I to L, Ci, and this is the measure of the ball with center in A sub I of this wall. Okay? In this way, we can compute the integral of a test function. So now we have two questions. The first one is, can we integrate more general functions? And the second question is how to compute or calculate volumes or measures of arbitrary subsets of QPA. Okay, let me take a break, guys, 10 minutes break, and then we come back. Okay.
Wilson, may I ask you a question?
Sure, Vladimir, go ahead.
Wilson, do you hear me? Do you hear me, Wilson? Wilson, do you hear me?
I cannot hear you very well, Vladimir. Could you please?
Okay, now do you hear me?
Yes, yes, go ahead.
Yes, okay. I have a question, but not about the lecture, that lecture, but about a future lecture. Do you plan to speak about Hensel's lemma? Will you mention it or not?
No, I am not going to cover the Hensel lemma. Sorry, Vladimir. I don't have time. I'm going to explain just integration today. If you need the Hensel lemma, probably you have to give an explanation.
Tomorrow, because I will need this lemma in my talk, in my lectures. If not, I will tell some words. If yes, then just let me know.
Please, Vladimir, include the Hensel lemma in your presentation, because I'm not going to cover the Hensel lemma today.
Okay. Thank you.
Okay. See you in 10 minutes.
Okay. There is another question about the motivation for the name of test functions.
Okay, good question.
So why is that those functions are called test functions?
The reason is the following. In the classical, in the standard literature, the characterization, or the main characterization of this function is that this space is invariant under the Fourier transform. And this space is also invariant under the Fourier transform in the p-adic frame. For that reason, that's the main motivation for calling these functions text functions. 10 minutes, 14. Estoy avanzando muy lentamente. Voy a tener que, es que es mucho lo que hay que escribir. Oye, yo voy a tener que poner, llevo 23 páginas. No, no, pero... No, me estoy saltando cosas. El problema es que no voy a alcanzar. A ver. Sí, que la física sí.
En eso, porque ustedes releyendo la otra cosa que en compactos
sí, en la medida de un compacto es finita.
Eso sí, es cierto en cualquier medida de Haar o es
en cualquier medida de Haar es cierto.
La otra pregunta era cuando la ley. Sí. La medida de cuenta se podría que me pregunto si el QP puede ser
No, es una medida de Borel. O sea, lo que decía era que el teorema de Haar tiene dos partes. La primera parte es que hay una clase especial del subconjuntos que es la simetría de Borel. Y esos son los que puedes medir.
Pero parece que más se superan en carácter.
Sí quiere decir que conjuntos más raros se pudieran medir.
Claro, más allá que la
pues la verdad no he trabajado en eso. Tal vez, pero no sé. No, tal vez, pero no sé la razón.
Pues la racionalidad
de
esa función.
Mirando a ver si.
Otro campo
son los borelianos. Sí, es medida estándar. Es teoría de la medida estándar.
Sí.
Sí, como exactamente. La medida de Lebesgue es una medida de Haar.
No, pues.
Me pregunto yo.
Es las series formales de Borel con de hecho, pues, el marco mediano solo es QP.
Es la medida de la bola de radio.
Si tú
es uno, sí.
puedes observar.
No, es de radio cero, Porque bueno, radio, depende. Acuérdate que yo escribo nada más el exponente. P a la 0 es 1, sí. Sí, de radio.
El plano es como la elección
De la medida, sí.
Ajá. Cuando el campo
Yo creo que voy a poner las transparencias.
ya es seguro.
Hay que decirle al técnico. Oye, yo creo que voy a tener que poner las transparencias.
Después de encontrarte con el resultado de cruzar,
¿Cómo lo pago?
la racionalidad de la Z debería también estar en Z. Porque uno puede probar para cierta familia de funciones
Bueno, para
por ejemplo, los resultados más importantes para la ¿quieres que hacer de la Z racional pero ya desde ya ahora es de las familias más grandes. Pero han habido otros resultados más generales. Parece que y aparte las pruebas son porque parece. Pero pues las cosas van a cambiar la física, pero son entonces ya mi tesis va a sobre eso, pues, de probar la racionalidad para otro tipo de que se llama singularidades. Y logré probar que era racional para ciertos singulares simples, pero no. Porque llegó un momento en donde ya de las matemáticas.
Hacer ejemplos de integración. Sí tienes razón, ¿eh? Sí tienes razón. Gracias. El grafete cada vez que se mueve, está muy atento. Sí, porque algo que sonaba ahí, decía, ¿por qué es? Sí, mándenle las transparencias. Ustedes tienen presentaciones, mándenlas para decirle a Estela que nos sube. Por favor, sí, muy lento. Voy a tener que usar. Déjame volver.
Wilson, lo que pasa es que me está explicando que hay una limitación.
Sí,
es que en el momento que bajas la pantalla, la cámara no funciona. Esto quiere decir que lo que puedas escribir aquí no lo van a ver en el mundo.
Bueno, déjame, voy a intentar ahorita, digamos, la siguiente hora con esto, ¿no? Y a ver cómo me... Hagámoslo así.
Cuando me viene yo voy a dar gente que pregunta entonces tienen el túnel H de medido.
Edwin, ¿me escucha?
Sí.
Voy muy despacio. Pues se supone que para mañana ya había cubierto algunos, por ejemplo, calcular una función z local o algo, y voy muy despacio. Entonces voy a tener que colocar unas copias escaneadas de mis transparencias Si ve que algo no se está viendo bien, me avisa, ¿no? Porque si no, o sea, para mañana su curso y esto va a estar complicado. Entonces voy a tener que acelerar el paso.
Ok.
¿Sí me escuchó?
Sí, está bien, vale.
Sí, si ve algo que sale de poco o alguna cosa así, porque vamos a...
Entonces van a mover la cámara, ¿verdad? Se va a enfocar la cámara ahora
No, la
o la van a
cámara,
poner
no,
al
dice
lado.
que la cámara no va a funcionar. Se va a ver directamente la presentación del computador.
Ah, ok, vale. Se va a compartir la presentación del computador aquí en el Zoom. Ok, vale, yo le aviso.
Ahora sí usaré. Hubo un debate por lo de Reino Borrell aquí, pero yo como que no te.
A ver quién es el
pero esa fue la pregunta. Y luego Fernando dijo, no, es una contradicción, ¿no? Más cosas. No, aparte que no, bueno, si no quedas esto de Trump, si quieres, luego este chico también dijo a la pregunta esta de que por qué antes entonces después
pues sí, también se les puede llamar.
Pero para que veas también alguna.
No, pero está bien, sí, no, si hay alguna cosa que no. Si hay alguna cosa que
yo te
un error, sí, por ejemplo,
pasamos, pero
en vez de sí, por favor, si en vez de colocar diferencia de contexto, sí, no, pero eso está bien.
¿Cuál archivo?
El archivo es y vamos a la página. Vamos como a la página 24. O la página 23. Página 23. La siguiente, perfecto, esa es. Y el control también. Si la pregunta de si yo apunto, ellos si o sea, si yo lo hago con el pointer, para eso, ellos, la gente, el internet lo ve, no lo ven. Tendría que hacerlo. Y si me paro aquí de todos modos tampoco lo van a ver. Sí, porque si uno no ve, pero así. Tendría que aproximarme a la computadora para señalar algo. Sí.
I have sent out your role every asked to. Ah?
Guys. Okay, guys, I'm moving very slowly. I'm supposed to compute several periodic integrals today because tomorrow there are two new courses. One of them, the course on local set of functions, requires certain integrals. So for this reason, now I'm not going to write on the whiteboard. I'm going to just use the scanned copies of my handwriting notes. Okay? Sorry. So as I said before the break, now we have to answer these two questions. Can we integrate more general functions? So in order to do this, we have to consider open and compact subsets of QPA. So suppose that U is an open compact subset. So this set is a disjoint union of a finite number of balls. Of course, because due to the fact that the set is compact, first of all, due to the fact that the set is open, the set is a union of balls. Now, the set is compact. Then, oh, sorry. Oh my goodness. Because the set is compact, in this union, we have only a finite number of sets. Now, there is, why the union is disjoint? Here, we have to know, or you have to know, that in the p-adic world, for the intersection of two balls, there are only two possibilities. The balls are disjoint, or one ball is included in the other. For this reason, in this union, we have disjoint union. Okay. Now, again, if we use this hypothesis that the set is compact, we can select just one radius. Okay, this is a standard reasoning in analysis. Now, this symbol, CU, the complex numbers, denotes a space of functions. More precisely, the space of continuous functions defined on U. So an element F in this space is a function with domain in U, taking values in the field of complex numbers. And in addition, this function must be a continuous function. Also, the support of the function F, is by definition the closure. This line, the bar means the topological closure of the set of points in the domain such that f of x is different from 0. This is the support of the function. The support of this function must be a subset of U. So an element f in this space is a continuous function with support contained in U. Now, let us take a function f in this space of continuous function. Then, this is a continuous function defined on a compact set. Then, this definition, the supremum of the absolute value of f of x when x belongs to U, this is a finite number. Okay? Because a continuous function in a compact set is bounded. Okay? It is not difficult. It's an exercise to show that this symbol is a norm. Okay, so this pair, the pair consisting of the continuous functions defined in U with this norm is a vector space, and this vector space is complete with respect to the distance induced by the norm. So this is a Banach space. Now we need another ingredient, du. Du is the space of test functions supported in U. So a test function phi can be represented as a linear combination of characteristic functions of poles. Okay. Now this function, the omega PL absolute norm of x minus a. This function omega is the characteristic function of this ball, of the ball with center in AI and radius p to the L. Okay? The support of the function phi is contained in the set U if and only if all these balls are contained in U for all I. An important part is that the space of test functions supported in U is dense in the space of continuous functions. What is the meaning of this? Suppose that f is a continuous function defined on U. Then there is a sequence n in this space such that the sequence converges to f in this norm. In other words, the distance between xn and f when n tends to infinity is 0. There is a problem with the microphone. Okay, comments or questions about these definitions, guys? Now, we know that we know how to integrate test functions. In particular, we know how to integrate test functions supported in the set U. So we know that this mapping, the mapping that sends phi in the integral of phi, is a well-defined linear function. This is the meaning of the linear property, okay? In this expression, A and B are complex numbers. Now, we want to extend this integral. The integral is defined only in the space of test functions. Now, we want to extend this integral, this functional, to the space of continuous functions defined on U. In order to do this, we take any function, any continuous function defined in U, and we know that there is a sequence of test function converging to F. We know how to integrate phi m. Then we define the integral of the function f with respect to the higher mentioned as the limit when m tends to infinity of the integral of phi m. Okay, this is a definition. Now, in order to show that this definition is correct, it is necessary to establish two things. First of all, we have to show that the limit when m tends to infinity of the integral of phi m exists. And second, we have to show that we can use any sequence converging to f. If we establish these two facts, then the definition that I gave before is correct. Otherwise, the definition is wrong. Okay? First of all, in order to show that the limit m tends to infinity of the integral of phi m exists, first, the first step to show this assertion is to notice that this is a sequence of complex numbers. This sequence is a Cauchy sequence. Okay? In order to show that this sequence is a Cauchy sequence, then we have to compute the difference between two numbers of this form. Then that difference can be written in this way as the integral of phi m minus phi l. We are interested in the distance between these two numbers. For this reason here, we have to put a complex norm. Now, we have to remember that this expression is bounded by the integral of the norm of phi m minus phi l. And now, this function, this integral, is bounded by the supremum of, by this supremum. Now, this is just the norm of phi n minus phi l, and the constant, the constant c is the volume of the compact set U, and this is a finite number. This integral exists because the set U is compact. Now, due to the fact that this sequence is a Cauchy sequence of complex number, then this sequence has a limit. In this way, we establish, the first fact that we need to show that the definition is correct. Now, the second part is not included in the notes. Let me see. The second part is not included in the notes, so we can do this as an exercise later, because now I cannot write on the whiteboard. Okay. Let me see. Okay. So right now we know how to integrate functions, continuous functions with compact support. The next step is to compute volumes or measures of arbitrary sets. In order to do this, I'm going to use the traditional approach, which is to explain the formula for changing variables in an integral. Before that, I need some remarks about series. Okay? This is the Professor Di Germes explained these ideas in the morning, but anyway, I think it's a good idea to review this fact. Okay. First of all, what is the meaning of this symbol? The meaning of this symbol is exactly this. In this, where AI are periodic numbers. This series converges, the series from I0 to infinity of A sub I converges if and only if this symbol represents a periodic number. Now, there is a result that says that this series is converted if and only if the general term satisfies this condition, if the limit of the absolute value of the general term when I tends to infinity is 0. I think this example was presented by Professor Di Germes in the morning, so I'm going to skip this example. Okay? Comments or questions? Yeah, sorry.
It's about some question of notation, about the notation du. If I'm not wrong, du is the space of test functions with compact support.
Du, yes.
Okay, so my question was about the symbol dqpn.
dqpn is the space of function. Du is the space of test function supporting du, and dqpn is just the space of test functions.
Oh, okay.
Now, I need some ideas about power series. So, in this framework, I is a multi-index, okay, and x to the I means this product, okay. So, an expression of this form. I'm talking about the first line in page 33. I think that the people online cannot see the pointer. The first line in page 33, the expression in the first line in page 33 is a formal power series. A formal power series is said to be convergent if there is a positive real number p to the r, such that the series converges this series, the series I in over the I, ci, 8 raised to I, converges for any vector a in QPN such that the norm of the vector is less than p to the r. Okay, this is the definition of convergent series. Now, suppose that we have a series, a formal power series, but now with coefficients in R. Okay, what is the meaning of this symbol? The meaning of this symbol is that x is a real value. Okay, in the first line, page 33, x is a periodic value. So, this is an element in this ring. This is the ring of formal power series of real formal. This is the ring of convergent power series. We say that a real series, here is missing real, is a dominant series for a periodic series, if and only if the periodic norm of Ci is bounded by A sub I super C. And this is valid for every I. Now, there is a result that says that a formal power series is convergent if and only if it has a dominant series. Okay? This is a general result. Let me give you an example. Let us consider this power series. Okay? Now, in this series, A sub I is an element in this ball. Notice, it's an element in this ball. Here, absolute value of I means the sum of the entries in the vector I. This condition means that the absolute value of AI is less or equal than p to the minus the norm of I. So in this example, the purpose of this example is to show that f of x, that this series converges in the unit ball, in the n-dimensional unit ball. So let us take a vector y in the unit ball. So y has this form. The condition y belongs to the unit ball means that the periodic absolute value of yi is less or equal to 1 for any I. Then the product of these absolute values is also less than or equal to 1. Now, this series, the series over the I, a sub I, y super I converges. Why? In order, in order to check the convergence of this series, we have to compute the norm, the pairing norm of the end of this term. Okay, so we have to compute the norm. So it's the norm of AR times the norm of this monomial. So in this expression, now we have to use we know that the norm of A sub I is less than P raised to the norm I, and the norm of these monomials is less than 1. So the conclusion is that the pairing norm of this expression, which is the general term in this series, is less than this power. Okay, now we have to compute this limit. This is the limit of the norm of the general term in this series. Now, by using this inequality, we can conclude that this limit is 0, which means that the original series converges for every point in the n-dimensional unit ball. In other words, we have this function. We have a function with domain in the n-dimensional unit ball with values in the one-dimensional unit ball, and this is the definition of this function. And this is a well-defined function. This is an example of a p-adic analytic function. Now I have to say something about analytic functions, p-adic analytic functions. Suppose that U is a subset, an open subset of QPA, and H is a function with domain in U, taking values in QP. We say that this function is analytic in U if this function can be represented locally as a convergent power series. More precisely, we say that H is analytic in U if for every point B in U, B is a vector, there is an open subset U tilde. U tilde is a subset of U, and the point B belongs to U tilde, and a convergent power series such that the value of the function h of x can be written as a power series with center in B. Okay, and this series is convergent for any x belonging to U tilde. Okay, this is the definition of p-adic analytic function. Now, in this case, we can compute the partial derivative of the function x with respect to the variable, say, xl. And we compute this partial derivative by this rule. In other words, we exchange the partial derivative and the series. The key point is that this series is a convergent power series. Okay? It's a convergent power series. Comments or questions about this definition? Yes, sure.
Definition of convergence of series in previous one.
Yes, you want to see the basically, let me come back. A formal power series is convergent if and only it has a dominant series.
No, I mean a definition of a series is convergent.
Okay.
So this one, I mean, by its nature, it defines converges like this. Yeah, I mean, we are giving a formal power series.
You have a formal power series, you say that it's convergent?
Why we want to define the convergence of the series like this?
Yes.
It's not,
so what is the meaning of the definition?
yeah, I mean, why do you need to keep some real numbers here? Why do you need to do that?
What is the meaning of this definition? This definition says that this formal power series is convergent if we can replace x by a vector in some ball around the origin, and the corresponding series is convergent. Even one more time. This series is convergent if we can replace x for any vector belonging to a unit ball around the origin. That's the definition of convergence in this frame. And this is a general definition. This definition is also valid on the complex case.
You just want to make sure that the series doesn't have just one.
Exactly. That's the key point. The series is convergent in more than one point. It's convergent in an open in an open set around the origin. Otherwise, this definition is not useful. So notice that in this definition, there is a translation. You see? X minus V. Okay. Now suppose that U and V are open subsets of QPN, and H, capital H, is a function from U to V. Okay. In this case, H can be written in this way. So H has n component. H, capital H, is a vector. We say that capital H is analytic if each entry is analytic. Okay? In this case, we say that H is analytic or an analytic map. Now, we say that capital H is bianalytic if H and H inverse are analytic. Basically, a bianalytic map is a change of coordinates. This is the key idea. The change of coordinates are bianalytic maps. Okay, this is the theorem that we need to do the calculation. Suppose that K0 and K1 are compact subsets of QPN. And suppose that there is a bianalytic mapping H between K1 and K0, such that, notice that the partial derivative of xy with respect to y, the partial derivative of hi with respect to yj, here we are assuming that capital HI is a power series. And then we know how to compute this derivative. Okay? This is just the Jacobian matrix of capital H. Now, the determinant, we assume that the determinant of this Jacobian matrix is different from 0 for any point z in K1. Okay? Now, suppose that we have a function defined on K0, a complex value function defined on K0. And we are interested in the integral of this integral, the integral of f over K0 with respect to the Haar measure. And we want to perform a change of variable. This is the change of variable. X is capital H of y. So this is the change of variable. By using the change of variable, the new domain of integration is K1. We have to replace X by capital H, y. Now, this is the new measure. Notice that the new measure is the periodic value of the Jacobian of the Jacobian determinant times the Haar measure. Okay, this is the formula for the change of variable. This result is valid in any locally compact ideal group. One important thing, guys, about this definition. Notice that we are integrating a complex valued function. But the change of variables is a function from QPN into QPN. This is important. Okay?
Why we need that the product, this condition, the product of K0.
What do you mean?
The first let K0, no, it's not a product, it's just K0.
This is the definition of
I thought that it was like a product of
no, this is H1, H2, Hn, but capital H.
No, it was just about the beginning. Let K0 times K.
No, there is a comma here. There is a comma. This K0, comma, K1, subset of QPN. Okay. Now, calculus 2. Now we can do calculus 2 using this formula for changing values. So this is the first exercise, to compute the volume of the ball with center at 0. When the center is the origin, we do not write the center. Okay, this is a convention. Okay, so this is the n-dimensional ball with radius r, which is the set of points in QPN such that the norm of x is less than or equal to p to the r. Okay, remember that the meaning of this symbol is max is the maximum of the absolute value of xi. Now, this is an exercise that really this ball is a polydisk. The meaning of this assertion is that this ball is a product of balls. So this ball is the Cartesian product of this ball, and it is a good idea to use this notation. Okay, here you have the notation using the absolute value, and in this line you have the notation using ideals. But this is very convenient. Why? Because we want to change variables in asterisks. We want to compute asterisks. In order to change variables in asterisks, we use this representation. Xi is p to the minus r times yi. Okay? And this is the change of variables, and I takes values from 1 to n. We have to compute the new measure. Okay? So we have to change the measure dnx by this measure. We have to compute the Jacobian of this transformation. It is not very difficult to compute this Jacobian matrix. It's just a diagonal matrix. Okay? And the elements in the diagonal, any element in the diagonal is p to the minus r. Okay? Now, if we compute the determinant of this matrix and then the periodic absolute value, we get p Rn. And this is the hard measure in terms of the variable. Now, we have to replace this expression in asterisk, and we get this expression. P to the Rn is a constant, so we can take this constant out of the integral, and now we have to compute the integral of the unit ball, but by convention, the volume of the measure of the unit ball is 1, so the volume or the measure of this ball is P to the Rn. Okay. Now, in the next example, we compute the volume or the measure of the n-dimensional sphere with center at the origin. This is the definition. This sphere consists of all the points in QPN such that the norm of S is exactly P to the R. The point is that this sphere can be represented or can be represented as this difference. So if we want to compute the measure of this sphere, the measure of this sphere is exactly the difference between the measure of these two balls, which is this expression. Now we apply the previous calculation and we get this line, the last line. And if we do a simple calculation, we obtain this result, okay, which is the announced formula. The volume of the n-dimensional sphere is P to the Rn times 1 minus P to the minus 3. Comments or questions? Now, something interesting. This is an example of a local zeta function. Okay? So right now we are interested in this integral. We are integrating x is a vector in the unit ball, n-dimensional unit ball different from 0. S is a complex variable. We need the condition that the real part of x is greater than 0. This is important. This condition is important to assure the convergence of this integral. The purpose of this exercise is to show that this integral has a meromorphic continuation to the whole complex plane as a rational function of p to the minus x. More precisely, this integral is given by this formula, and this formula is valid if the real part of x is greater than minus n. So we can use this formula to give values, to give a value of this integral for any complex number x. This function is meromorphic because this is a rational function in p to minus x. The integral, this is the original integral. The original integral agrees with this meromorphic function only in the half plane real of x greater than minus n. So this rational function gives a meromorphic continuation of the original integral to the whole complex plane. Okay, it is important to read this remark. What is the meaning of the complex power of the absolute value p is exactly this. Okay, this is a local zeta function, and tomorrow Dr. Edwin Leon is going to start with a mini course on local zeta functions.
What's on the exponent?
We're exponing, where?
That's the quality, exponential of.
What is the meaning of this? It's exponential of x natural logarithm of the absolute value of the norm of x. Yeah, and this is valid for x different from 0. Okay. Okay. Now, any vector different from 0 in the unit ball can be represented as a power of p times another vector x tilde, but the norm of x tilde is 1. Okay. The norm of this vector is p to the minus r. Please note that here you have r, and in the norm you have minus r. Now, this means that x is a point in this sphere. Pay attention to minus here, minus here. X is a point in the n-dimensional sphere of radius minus r. Now, any vector in the unit ball is different from 0 can be represented in this form. For this reason, the n-dimensional unit ball minus 0 is the disjoint union of spheres of this type. But now R runs from 0 to infinity. Okay? So if we want to compute the integral over this set, we can use this decomposition. Then the integral over this disjoint union is a series, the series from R from 0 to infinity. Now we have to compute the integral of this function, but now the domain of integration is this sphere, the n-dimensional sphere of radius minus r. In other words, we are integrating over the set of x such that the norm of x is exactly p to the minus r. Okay. Now notice that this function, the integrand, is constant on this sphere. More precisely, the value of this function is p to the minus, the value is p to the minus rx, and now we have to compute the volume of the n-dimensional sphere of radius minus r. We know this integral, the value is this expression. Now we obtain this expression. At this point, we have to remember a well-known result about geometric series. So this series converges if and only the real part of x plus n is greater than 0. In other words, if the real part of x is greater than minus n, and now this is a simple calculation.
Where is the integration arrived from during the previous stage? The function. I mean, yeah, this function. I mean,
you mean by this?
I mean, in previous last page. Previous.
Okay, let me go back.
Oh,
we are integrating this function. We are integrating this function. We are integrating this function, and this function depends on a complex parameter. So, after using this formula, this integral becomes a series, and we have to integrate this function, the original function, but now the domain of integration is a sphere. The point is that this function, the integrand, is constant on this sphere. You see? Here you have the absolute value of p, and the absolute value of p is p to the minus r. So this function, this number is p to the minus rs times this volume. And then we know, we already computed this volume. This volume is given by this expression, p to the minus rn times this number. Now, we write this series in this form, and here we have to remember the geometric series. Okay? By using the geometric series, we can compute the value of the series.
Yeah. I think the question was why that is the formula for the zeta function. Why you define that as a zeta function?
No, this is different. Okay.
And I feel that the answer is because instead of sum, we are considering integration.
But don't worry about you. Tomorrow, you're gonna get the answer. Tomorrow, you're gonna have. I mean, there is an entire course about local zeta functions. My purpose is just to show you an example. But if you want to know the answer to that question, you have to attend the course of Dr. Leon Carolina. Okay?
And then you said that this is a meromorphic function?
No, the integral has a meromorphic continuation.
Meromorphic continuation
To the whole complex plane.
You get this function as a variable p.
No, it's t to the minus x, and x is a complex variable. In this integral, s is a complex variable. So this expression is a meromorphic function. This is a function of one complex variable, which is x. For this reason, this is a meromorphic function. The standard sense. Here, this is just complex numbers. Here we are in the domain of the complex number.
But here you only tend to for real numbers.
For real, no.
Numbers.
For complex number with real part greater than minus n.
But above you say you can check to the whole complex.
Of course. No. What is the? Okay, pay attention to this, guys. This object is an integral. The left side is an integral. At the beginning of the calculation, we know that this integral is convergent if the real part of x is greater than 0. We did the calculation. This integral agrees with this function only in this half plane. This equality is valid only in this half plane. Now you can say the following. If this variable doesn't belong to this half plane, you can use this formula to interpolate to give a value to zs.
Right. So the whole complex, but not all C, not all complex. Just for the part, real numbers, real part will be greater than.
Yes, the integral. What is the meaning of this line? The meaning of this line is the original integral exists only if the real part of s is greater than minus n.
But the other function.
If x doesn't belong to the set, the integral doesn't exist. But you can say, look, I can interpret the value of this integral using this function. This is an meromorphic continuation. Okay, let me check that.
So another question is that so far you use the values of your functions are in the complex function. And makes sense. My thing is that you are just using that the complex numbers are complete and you have a metric.
No, but we are not using that. I mean,
you use for convergence.
No. The point is the first step is to show that this integral exists.
No. I'm not talking about the integral. I mean, the values of the functions that you are integrating are functions.
The values are complex numbers.
The only thing that you're using of complex is that you have a complete field with a metric.
Yes.
So you may generalize this as
Yes, I understand. No, this is more complicated. Yes, it is possible, but this is more complicated. There are other, in that case, there are other problems that you don't have in this classical sense. That's the case that you're mentioning is more complicated.
I know. But the definition will work more or less.
More or less, but that case is more complicated. Okay, let me. The time I have. 10 minutes. Okay, thank you. Guys, let me. Okay. Okay, I have to show you something extremely important.
So here, this one as well as this. So this is your combination. So you're in simple. Yes, the geometric series doesn't go only one without part, but this expression we can use it we want
Guys, please do me a favor. Go to the file, my file, and I need an example about the computation of the Cohen-Nielsen amplitude for 4 points. I cannot find. Let me see. This is an exercise, but okay.
Example 4.9.
What is the number of the example? 4.9. Could you give me the page? I need the page.
194.
194. The page in the. No, I need 194 here now, but let me see. No, no, it's
like 10 pages. Very 205. 206.
195, 194.
It's 194.
It's page 19 in the PDF.
I told you that.
Guys, this is an extremely important example. I need this example. Okay. This integral, okay, in this integral, capital N is a number, it's a natural number weighted on 4. This represents the number of particles with a certain interaction. These numbers, x, 1j, and x, ij, are complex numbers. P is the number of these variables, okay? So this object is a periodic Cohen-Nielsen local zeta function. It's basically a periodic Cohen-Nielsen amplitude. There is a course on string amplitudes, okay? So I have to present it. And we are going to have also a conference about this amplitude, okay? This is a Cohen-Nielsen string amplitude, okay? This is basically a periodic integral, okay? In this example, we are interested in the case in which n is 4. In this particular case, this formula takes this form, the form 4.1. The purpose of this exercise is to compute this integral. Probably I'm going to stop here because I'm going to do this tomorrow with certain detail because this is important. Okay, so I suggest that you review this calculation and we can talk about this calculation tomorrow. Okay, guys, I'm going to stop here. Do you have comments or questions?
I just have one question about notation. In this very example, it uses the word regularize. What do you mean by this?
Okay, regularization. The point is, okay, what is the expression? Okay, this is a situation. In physics, in higher level physics, there are some integrals. Regularization means to make sense of the integral. You have to, in sense, to provide a correct definition so that the integral makes sense. But do not worry. We have a course on string amplitudes and we have a conference. Okay, guys, do you have more questions? Okay, so tomorrow I'm going to do this calculation and I'm going to do more integrals. I'm probably going to use the whiteboard. Okay.
Okay. Thank you, Wilson, for your.
Bye-bye.
Okay, so now we have a break and we will come back at 5:30 for a talk by Gosh and Sydney.
Si quieres para la grabación.
Para la creación.
No, es que eso. This is true. However, you can find the function that are equals one and dot. It's defined everywhere except for and this is only defined in data, but this is defined in the default. This is what he's doing. He's taking the right hand side that is defined out of all the complex length and giving out the definition for the concept. He means by using the integral. This is the same.
La fórmula le va a servir. Si es abeliano.
No, I know that.
Déjenme mirar. Espera un momentico. Quiere hacer un cambio de variante. Déjame pensar, porque si no hay un detalle. No, hay un detalle importante, porque esa fórmula y en un contexto como este, no necesariamente tiene una serie de definiciones. Pero hay una fórmula, eso existe. O sea, no, busca, hay un libro, se llama Fourier Análisis. Fourier Análisis, análisis. Es el amigo como ese, porque lo que le presenté es esto. Pero si mira la referencia sobre hay un menciono que puede ser amigo como este para pero yo utilizo serie de potencias. O sea, lo que pasa es que cuando pero ¿qué hipótesis tienes sobre la? Porque podría ser que la E. Ah, no, si es R, no, si es R va a funcionar. El problema es que tiene un común abstracto. Ah, no, R funciona la que yo digo. No, ese funciona la que yo digo. Sí, no, sí, debe funcionar la que yo digo. Debe funcionar. Sí, debe funcionar la que yo digo. Debe funcionar. Sí, pero hay la integración. No, todo eso es discreto, ¿no? Donde tiene que tener un factor que sea, tiene que ser un factor que tenga una medida de actividad.
¿En qué universidad?
Pero ¿qué integración lineal? Z. Z, a ver, la voy a dejar. Ese es un grupo, sí, es un grupo topológico. Lo que pasa es que es un grupo lo que pasa es que también es una medida discreta. Ah, no, bueno, la función de es una suma de deltas de Dirac.
Será más analítica, será más intelectual.
Tiene que fibrar, ¿no? O sea, en general, pues supongamos, se puede fibrar. Fibrar significa que Hello, Codor. How are you doing?
Hello, good. Hi, Wilson.
Congrats. Last talk. What do you think?
There are some interruptions.
Okay, are you ready?
I'm ready. Yeah.
Okay.
Okay, so shall I start? I see you froze. Okay, can you hear me? Can you confirm, Wilson, that you can hear me? Hello? Hi, Wilson. Hi,
Hello, Rodor.
hi, Wilson.
We have a problem with the internet. The technicians are trying to fix the problem. Look, let's say 15 minutes. If the problem persists, I think the solution is to move the conference to another day. For instance, I'm considering that you can give your conference as a two conference, which is let me see, Tuesday 21st. That would be okay for you?
Tuesday, what time?
But Tuesday after, okay, is okay. The problem would be 3 p.m. 3 p.m.
3 p.m.
Yes, 3 p.m. or probably after the lunch. No, 3 p.m. 3 p.m.
Actually, 2 I can't tomorrow. I have a meeting like.
No, it's Tuesday 21st. The 21st at 3 p.m.
21st. Today is 23rd.
No. No. I'm talking about Tuesday, May 21st, the last conference of the school.
31st, you mean? The last day.
The last day, exactly.
So let me see.
I mean, this is the last resource possibility.
Would it work on Monday? Because I'm traveling the next day. I can, in principle, I can make it work on Tuesday. Yeah. Anyway, yeah, we'll make it work if the problem is not fixed today. And then we agree on a day between you and me.
Okay, perfect.
Yeah, no problem.
Because right now we're trying to fix the problem. So let us wait
until 6.
10 more minutes, 15 more minutes.
Yeah, that's fine.
Please, if we do not fix the problem, then we find another day for you to talk.
All right. Okay.
Okay, sorry, Trump,
yeah, no problem. Yeah.
It's the one technical problem.
Yeah, that's the. I mean, doing things online makes things easier, but they come with a price.
Okay, sorry.
Yeah, that's
okay.
Fine.
So let's wait 15 more minutes. If we don't solve the problem this time, we will have to cast it off.
Okay.
Okay.
That's
then
fine.
We find another day for to talk.
Okay. Yeah. Then we can try to find. That's fine.
Okay. Okay.
Okay.
We can put in 15 minutes. If the problem persists. Okay. I'm going to call you in 15 minutes.
Okay. All right.
Fix the problem.
Yeah.
Okay.
All right.